It's always good to be last in line, so people are either here because they want to or getting ready to leave. We're going to cover some territory today talking about advancements in platinum substitution alloys for medical components. Johnson Matthey over in booth 2321. So we're going to start with a quick review of current applications and move over to why people use platinum alloys. And then we'll have a short discussion on why we want to move away from platinum alloys and look at platinum substitution, mainly driven by the prices. And we'll talk a little bit about what drives those prices. Then we'll talk about palladium and some of the palladium substitution alloys that we've been working with and talk about the advantages and maybe some of the disadvantages. Talk about some of the manufacturing capabilities, and then we'll call it quits. So some of the benefits of platinum, of course, are it's the metal of choice when you have heart disease, stroke, chronic pain, mainly because it's inert, does well in the body, and of course, radiopaque. Some of the common uses for platinum in CRM are pretty wide, and most people in this audience would know most of these. Everything from pacing tips to electrodes to the feed-throughs. Some of the other areas that have gained use over the last several years are, of course, in cochlear ear implants as well, where the platinum is inert, provides excellent conductivity, and of course stays in the body. So some of the things that we all know and like about platinum group metals, of course, are their chemical properties specific to corrosion resistance, physical properties based on radiopacity, and electrical properties. Of course, it's an excellent conductor in the body, and we can tune the mechanical properties, everything from fully annealed to full hard condition, so we can match whatever the requirements are for use in the body. What's driving platinum substitution alloys? Mainly it's the cost. Platinum alloys, of course, have gone up. It is a commodity. We can also go to lower density alloys that give more yield per unit weight. So if you're looking at a wire-based product, you can sometimes get up to 70% more feet for the same weight of precious metal. And because we've worked hard to maintain the properties, we can also tune the radiopacity. And I'll show a slide later that shows that we can have equivalent radiopacity using palladium-based materials when compared to platinum-based materials. So here's a long history of the platinum and palladium prices going back to 1992. And you can see we've had a couple of spikes in 2000. And over the last couple of years, it's pretty much been out of control. Yet palladium prices have remained lower than platinum. And I have some information on what drives these prices. So we have a group that specializes in platinum metals and forward-looking, and they provided this information for us. Some of the platinum price drivers over the last several months have been the speculative demand in the exchange-traded funds where people are investing in platinum, and it causes the volatility on the up and down. Most of the platinum products come from South Africa, and heavy rains and flooding have caused concerns over coal shipments, and when they can't get energy, they can't run their mines, and therefore we've seen a depletion in supply. We've also seen a recovery in North America on in Europe on heavy-duty diesel, and the platinum is used in the catalytic converters. And there's also been concerns over in Europe with the debt that's fueling speculative interest. So these are causing an unstable marketplace for platinum, which also continues to drive people over to palladium-based alloys. This information is available on our platinum.matthey.com website, where you can gain insight into what drives both platinum and palladium and all the other precious metals. So which alloys are in use today on the platinum side of the business? Currently, the most common alloys that are used are the platinum 10 iridium, the platinum 8 tungsten, and the platinum 10% nickel. These have been the mainstays for at least the last 30 years in the medical device industry, and I think all of us have a fairly good handle on where they're used and why they're used. In all cases, the iridium, tungsten, and nickel have been added for increased strength and stability. We have a whole family of platinum alloys that are available, even though the marketplace chooses on a couple. And I just listed some of the alloys that are available today commonly, all the way up to the platinum 30% iridium, which is very hard and difficult to manufacture. And we've expanded the Platinum family to include some of the high nickel alloys, where the nickel content is providing strength and reduced cost. As we begin to look at palladium-based alloys, what we're trying to accomplish is provide an equivalent material, and what we do is we swap out the palladium for the platinum, and of course the immediate gain is in density. It's a lower density material, lighter weight, so when you purchase platinum alloys, you're buying them by weight, you get more material. And how do we go about that? We take the palladium compositions, we add second phase materials to alloy in, typically nickel, rhenium, tungsten, or even platinum. And of course, Johnson Matthey does have a full department that can do custom alloy development if you see an alloy that you want that's not on the list. For the palladium families, we looked at what we know best, and we had a history of the platinum iridium, and we went ahead and just swapped out platinum for palladium, and we now have a family of palladium alloys with increasing content of iridium, and these materials are already available in the marketplace. And we went ahead and we also expanded and went to palladium rhenium alloys, where the rhenium is added for strength. We also have a palladium 20% platinum alloy that does offer advantages, once again, where you've got 80% palladium, so you've got a lower density material. And what this graph is demonstrating is that if you swap the palladium versus a platinum-based alloy, because of density, you gain yield. And I did this particular graph based on 0.127 millimeter wire, commonly known as 5/1000s. And you can see if you would switch from pure platinum to pure palladium, you would immediately gain almost 80% more yield just on density alone. So as we get questions from the field, we're able to look at the property required and gain knowledge and insight. I included a couple gold alloys here as well. Johnson Matthey does have experience with gold alloys. From a mechanical property standpoint, we have requirements for both fully annealed and hard drawn. And what we're looking at here is the ultimate tensile strength in megapascals of the variety of both platinum alloys that are common and the new families of palladium substitution alloys. Of course, the palladium is not quite as hard as the platinum alloys, but we're striving to continue to get better at making the alloys harder so we have equivalent properties. From an opacity standpoint, this was a radiograph we took of coiled wires, and it's comparing nitinol in the center with palladium rhenium, conventional platinum 10 nickel, and platinum 8 tungsten. And what you can see is that we can match the alloys from an opacity standpoint so that they have equivalent opacity, yet they're lower cost. From a manufacturing capability, we're vertically integrated. We're able to melt our own materials, fabricate them in the foil sheet and tubing. We can offer wire, rod, and bar stock. We can machine the bar stock and make micro components. And we also do the refining of the alloy. So we've got the cradle to grave. We can produce the alloy, we can recover it out the other end. Some of the future development we should be working on are beginning to catalog all the electrical properties of these materials, complete the gathering of the mechanical properties, and also complete the gathering of the physical properties. We've got some of these already posted to our website, and as we continue to gather this information, it will also be posted. We should also continue to expand the alloy families as we continue to tune the platinum compositions for specific applications that require palladium-based materials with lower cost and equivalent properties. So in conclusion, Johnson Matthey offers a wide range of platinum substitution alloys. We can provide custom alloy development to the marketplace, and we're capable of matching electrical, mechanical, and physical properties to the current requirements in the marketplace. And I'd like to acknowledge Johnson Matthey for supporting this, and special thanks to Stuart, the editor, who helped me put this together, and our engineering team who gathered the data and made it available to us today. And are there any questions? Yes?
Have you looked at or are looking at any tantalum material alloys as a substitution for platinum?
No, not currently. Come on, that's too easy. Yes?
Just a quick question. If you go back to the graph, you know, where you trended palladium and platinum over time, and you saw that spike with the palladium, do you know what caused that spike, historically speaking? And is there a fear of that happening again, potentially?
I'll have to ask some of my colleagues. John, can you answer that? And to answer the second half of your question, if you go to platinum.matthey.com, we have a whole separate division that specializes in the metal markets, and they focus only on the precious metal side, and there's a wonderful website full of information going back more than 15 years that talks about the markets, what's driving them, and where they're going. All right, then I guess we're done for the day. Thank you for coming.